tau volume or something, but I feel like what if I want to
make it look like a physical thing.
Yeah.
But I was like,
yeah, right. So
I don't want to do that because it'd be
one
fun.
way, I mean, this log function is kind of a
like making it look like a
very
proof or something.
Yeah.
right. So
I mean, that'd be really
that's
cool, but it's
kind of a way to get you started in the right
sure.
direction. But then you may, you know, if you actually
Yeah.
want to see how it's working, then
by the way,
log
on this
function is not
thing,
probably
I would
that's
even be able to be
way
able
to
to.
there's other stuff.
We don't have.
Sure, I mean, Thursday night,
And probably
my wife,
as
for her
long
nanny
as
job
you
is every other week, so she
have a way that makes
on
sense
Friday
and you,
night.
and you justify it on your implications.
No, I don't work on Saturday.
But there's like more granular way to.
Yeah, I don't mind working on
Yeah,
Thursday.
log value
I'll see if John can come too.
but it may not give you the end result.
It sounds like he's.
What is the log function? Like, where did
I
that
just want to make sure for sure we know like we're sending the same format. Sure.
Yeah, and I can make sure it's JSON.
Right.
Because everything that is going to get sent back should be.
Right.
So try to get that. I guess I'll read it or whatever, and then try to.
Yeah, but we honestly don't need to have it done for a long time.
No, like even if the next part of the assignment is even until the 22nd, and it's not even about stuff that they touch.
And I've almost got that part. I could probably do that report really easy because I addressed most of those issues.
Yeah, so it's kind of like.
No, I haven't actually collected a huge data set, but like questions like 2 through 5 I think address like you have to pre-process it, what considerations were there to make it faster, and we've done that. So, but we actually need to like download a bunch of MIDI files or something. Yeah.
Okay, so it's 3, so we should get started, even though I think this hopefully is coming on soon. To start, just some administrative things. So let's see. So the homework 1 grades were posted. I have not had a chance to look over them too carefully yet, but I will kind of do that soon and make sure everything's fair. There's at least one question that I think everyone got wrong, and according to the TA, and I said, you're being too harsh, so he either has or he will be giving some points back. And I think everyone only lost like 1 point on that one. It was like 4B, I think was the one. But I didn't look over everything yet. Let's see if this is, okay, maybe now it's coming on. Good. Let's see, and the next homework is not due for, so I think it's due next week. Does that sound right? The next one is due February 17th, so that's going to be next week, Wednesday. Okay. A lot of you have started working on that. That's great. It's kind of building on these idea of hash functions, but you're doing this with actual text and stuff we talked about in the last section of class. We are starting now today, and the next 3 lectures will be on clustering. Let me adjust something quick. Okay, so we're starting now on the lectures on clustering, and so these, this is kind of a very traditional topic that's associated with data mining, but it's also something that's very vague. So if you take a class, if you take a class in algorithms, it's all about these very extremely well-defined problems, that you're given a well-defined problem and you want to solve it quickly. Clustering is kind of like the opposite. It's a very, it's as a topic is very ill-defined. Just took away my colors. Okay, I'll put them there. So it's a pretty ill-defined topic. So it means every variation of clustering is solving essentially a slightly different problem. And there are many different sorts of problems you could want to define. And so a lot of the challenges in dealing with clustering is choosing what problem setup to run. So I'll try and, in this section of class, we'll try and cover like broad categories of these techniques. But there's many we aren't going to be able to cover just because there are so many variants. So let's start. So saying in particular, let's start with so let's start with kind of a formulation of what would be a hard clustering. There's something called a soft clustering, which is even more general than this. But you're starting with some. So you're given a set, which is the input, a set X, which is going to lie maybe in some sort of metric space. And you have associated with this some distance function, which goes, let's just say, generally between 2 points in this metric space. Okay? So this could be very generally any distance function, so that's why we talked about distance functions later, or why we spent a whole lecture on distance functions. It can really be anything, and for this, I'll assume that it's that this is going to be a metric. There's some clustering formulations where it's for things to work, it's kind of required for it to be metric. For others, you can kind of loosen this. I'll talk about this as it comes up. So then, a clustering is going to have 3 general properties to it. So property C1. So what you're okay. So let's see. So you're going to have something called a cluster, which is going to be a set, say Si, which is a subset of X. So there's also this term. This term clustering is used in other areas. So like in some areas of statistical spatial analysis, a clustering is going to be defined not as necessarily, well, okay, I'm getting a little bit ahead of myself. So a cluster is one subset of data, and then a cluster ring is going to be, we'll call this script C of X is going to be a S1, S2, up to Sk. So it's going to be a set of these subsets. And the hard clustering will have three properties now. So C1 is that each Si is a subset of X. Okay, that's what we said. It's a subset of the data. C2 is that each pair Si intersect Sj is going to be the empty set. So there are not going to be any intersections. So this is a hard clustering, so it's going to, things aren't overlapping. There are versions where you're allowed to overlap. We're not going to, if this is not true. Otherwise, then this is known as a soft clustering. And so then C3 is that the union of all I equals 1 to k of these SIs is going to equal our set X. Okay, so so in other words, you can think of this as a partition of the data. So you're partitioning the data up into these parts. So this is when we're talking about clustering, this is what we're talking about. In other areas, a clustering may be, you have a big data set and you want to find some particular subset which is tightly grouped together in some way. And you just to find that subset, the rest you don't care about. That's a useful objective in some places. Here we're talking about partitioning the data up into parts. So think, you could be like a common place where this comes up in like these large internet companies is this set X is all of your customers, and the clusters are different types of your customers. And you want to say customers in set S1 behave in a certain way. I want to target them with a certain type of advertising. I want to give those customers some ads. Or maybe customers in type 2 are the ones who spend a lot of money but don't make money for the company. These are like big spenders but are very savvy, so they only buy when there's a sale or something like that. Turns out this is kind of very useful and is not easy to do for most companies, and each challenge is different. There are different aspects, and really what differs here is the choice of the distance function that's using. How do you properly define the distance, among these customers? There's also a question of which general approach to use to find this clustering, and which objective you use to say how good is the clustering, right? This does not say how good is the clustering. What I could have done is I could have made S2 through SK empty, and then S1 equal to the cluster X, right? That's possible. I could have done that. That satisfies this formulation. I haven't told you anything about the objective of this, right? Objective is saying how good is the clustering, right? So I need it to satisfy these properties, but then I want to score it, right? So I'm going to score some clusterings better than other clusterings, and then I'm going to try and find clusterings which have a high score, or maybe a low score, depending on if I want to have it higher, right? Okay, so before I say anything specific, let's try and give some general principles about what is a good clustering or what is a bad clustering, right? So I'll start by drawing kind of a picture, and then we can comment various ways on the picture here. So let's say my data look kind of like this. Okay, so what would be a good clustering? What would make sense to be a good clustering? Let's hear from the class. Go ahead.
Just basically circle the three groups of dots that are close to one another. So
right, so these are kind of close to each other. These are kind of close, and those are close, right? Yeah. So let's go do that. Right. So I have these, maybe one cluster, another. So this would be S1, S2, S3. Yeah. This. So this kind of seems reasonable, right? Okay, so who's seen clustering like this before? Is this new to anyone? Okay, is this new to anyone, this idea of clustering this data? Okay, good. So, this is kind of a very common picture or sort of thing you'll see. This, if it data looks like this, it's not really that hard, right? It's, pretty much anything we describe will give you the same result on this data here. You're going to want these three clusters, assuming that you were told that you wanted 3 clusters. What if someone said, I wanted 4 clusters? You said, no, here are 3. No, I want 4 clusters. What should I do? You're working in a company, your boss says, I need 4 groups because I can put them in a box, in a square, and divide them that nice way. I want 4 groups now. You know, so now what do you do?
Create an empty group.
You could create an empty group. Yes, that's a good thing to do. Say new customers. You know, make something up. You know, that's probably a good strategy. But if he comes back and says no, that's empty. That one doesn't count.
I'd split one of these groups.
Yeah, so you can split one of these groups. So maybe you'll say, let's split this group here, right? Maybe say, okay, let's break this one up into, I don't know, maybe something like this, right? Sure. You know, that seems reasonable. Then you can make this S2 and S4. Okay, but this, now it's not so clear what is the right thing to do. Why did I split this group instead of this group over here? So, you know, this will depend on the formulation, and what result you get is going to depend. Also, if your data looks like this, you don't need to run an algorithm. Just draw a picture and circle it on the piece of paper, okay? The power in these algorithms is that they're going to basically just take in this data set and this distance function, arbitrary distance function, maybe as long as it's symmetric, and then they're going to run. So, you know, so they can deal with things where you get a lot of attributes, something more, you're measuring things more than just two-dimensional, like Euclidean distance in the plane. You could have a lot more clusters. You don't need to be able to see them to understand what's happening. But we'll draw pictures a lot in 2D because we can draw them in 2D and illustrate some things. But I'll try and point out, like there's this very famous picture that shows up in lots of papers where someone created this data set that looked like this, and then this paper claimed, and 100 other papers claim that the clustering should look like S2. They said, this makes more sense. And maybe they're a little bit further apart. I'm not sure if I drew it just right, but this picture itself seems like completely ridiculous to me. When is your data going to look like this, right? This is I don't know what they're trying to illustrate here, but this seemed like a very strange thing to happen. Your data is never going to look like this. Your data is going to be probably high dimensional. You're going to just have access to it through a distance function, and that's all you're going to do. You're not going to see something that looks like this on the plane. Who knows? And if it really looked like that on the plane, then take out your marker and draw a picture yourself for it. You know, so okay, so going back to this distance function here, so if you look back at this first example here, look at this example. Why was this first clustering, let me get rid of this S4, the purple one. Why did this make sense as the clustering? Why was this, what told you that this was good? What are the basic things you were after?
Distance between the points.
The distance between the points. What about the distance between them? What is good about this clustering with respect to the distance?
They're closer. The grouping are tight distance.
Yeah, so the points inside of the cluster are close. Good. So there's one is the points inside of the cluster. These distances are close. So this is often referred to, or sometimes referred to as the width. It's some function of the distances in the cluster. This is in the cluster, and this is you want this to be small. Okay, good. So this is one thing you're looking for. what else would you look for? Yeah.
Distance to the mean or median of the other points within that cluster?
Yeah, this is kind of, I left this description vague. It's something about the distances in the cluster, and you want that small. There's something else, yeah.
You would want to do the minimum number of clusters. You would want
A small number of clusters, yeah. So if you had some choice, if you were choosing K, you may want the number of clusters we often refer to as K, the variable. If you were choosing K, you'd probably err on the smaller side. If you could describe it just as well with the smaller K, that's probably better. Typically, the larger the K, the objective function is going to go down usually, and this is going to make it challenging in choosing what the right K is. And we'll come back to this at some other point. Let's assume you were given the value K. I was given 3, and now I chose these 3 clusters. One is I wanted within the cluster the width to be small. There's something else that's going on that you
Do you want to maximize the distance between clusters?
Yeah, so there's another thing going on here, that the distance in between the clusters, this distance, often called the split. So this is the distance between clusters. You want this to be large. Okay, so you want the width, which is the inside cluster distance, to be small, the clusters to be well grouped, and the split, which is the distance between clusters, how far they are apart, to be large. So you want that to be distinguishable, that there are 2 different clusters, that there's not kind of some confusion, and then within the cluster you want it tightly grouped. These are generally the 2 properties that you want, the split to be large and the width to be small. And there are many different ways of measuring these things. And sometimes you can write an objective with only one of these 2. Right? If K is fixed, maybe you only need to minimize the width and the split will take care of itself. Or maybe you just care about the split and the width you're not so concerned about if K is given to you. Okay, but there, as you started to say, like there was some representative point and you're talking about the relationship to that to define the width versus maybe the sum or all these distances. There are lots of ways to kind of define what these means. And so we'll kind of get into some common cases, but even trying to enumerate them at this point is just going to be kind of pointless. Really, you want to use one that works well with the algorithm, the general algorithmic technique that your algorithm is using, more so than whichever one. Maybe there's something about modeling it the best, something like that. Okay, so what we'll talk about today. Let me maybe just do it here. So we'll talk about, in general, we're going to have 3 types of clustering that we'll talk about in this part of the class. The one today is going to be hierarchical agglomerative hierarchical agglomerative clustering. This is probably maybe one of the first things you would think about how to do this algorithm. Maybe not, I'm going to expose other things, but it's kind of the simplest and most general, and a lot of things fall in this category. The second one is going to be, maybe I'll say, assignment based clustering. And then the third is going to be spectral clustering. So this one, the spectral clustering, the spectral refers to the eigen structure of a matrix. So if you, for this we're going to need to start talking about matrices more carefully and the eigenvalues and the singular values of them. And we'll come back to that much more later in class, but I wanted to talk about this now. What you do is you take your data, your distance matrix, or your distances of the points, you formulate that as a graph, which you then represent as a matrix, and then the matrix kind of tells you how to cluster the data using the eigenvalues. It's kind of cool, but it's going to be very different than what we'll talk about on today and Wednesday. On Wednesday, we'll talk about these assignment-based clusterings. This includes the k-means formulation, which probably many of you have heard of. Who has heard of k-means clustering and who's not heard of k-means clustering? Okay, so k-means clustering is often the first thing that people think of when they think of clustering, if they have been exposed to it. And it will be included in here. The idea with this sort of clustering is that each cluster gets one representative point, and that's enough to define the cluster. You map every data point onto the closest representative point. So you assign it to the center, and that's called the center, that representative point. So you assign every point to a center, to the closest one, and that defines the clusters. Okay? And so k-means is an example of this, where you use essentially the L2 version of this. There's a very cool algorithm called Lloyd's algorithm, which makes it very easy to optimize. But there are other variants of this which are sometimes even more useful or more stable on various. So we'll talk about this on Wednesday. Today we'll talk about this hierarchical agglomerative clustering. And so this overly complex word, so agglomerative means that you're kind of gluing things together. So you're kind of starting from the bottom up, and you're kind of building all the clusters, making them bigger and bigger together. In contrast, the spectral clustering will be an example of something top-down, where you start everything as in one cluster and you keep chopping it up into pieces. Okay, so this one is going to be top down, where you're kind of carving it up, and the one we'll talk about today is going to be bottom up, where we start with a bunch of really tiny clusters and kind of start gluing them together. Okay, so, and then the assignment-based clustering is going to be kind of neither. It's going to be something where it's based on these centers and you do a completely different approach. Okay, so these three classes, which will probably cover 90% of each class roughly, covers probably 90% of all types of clustering, but there's other types that I won't get to. There's things like mean shift, which is doing some weird things, and there's this density-based clustering where you try and find these where the regions of high density and anything in those gets in the same cluster. And we aren't going to talk too much about these, just because you can go on and on. There's a class that Suresh Venkata Subramanian occasionally offers. I think it'll be offered next fall. The whole semester is on clustering. So you could have a whole class on this sort of stuff. We're going to do basically 3 lectures, and then we'll come back to something related to it based on graphs. That's kind of different from both of these as well, based on something called modularity in one of the last lectures of the semester. Okay, so this hierarchical agglomerative clustering. Any questions? Any questions on this before we go on?
Really quick, could you explain again the difference between soft clustering and hard clustering?
Yeah, okay, so hard clustering restricts that any pair of clusters, say S1 and S2 here, they cannot share any of the points. Each point is assigned to exactly one cluster. So you can't, or that statement requires the third point as well, but each point is in at most one cluster is what the property to assign. Whereas soft clustering does not require that. So let's say that there was some data point, some other data point right here that kind of sits in between S1 and S2, and maybe both these are really well defined and they're denser. Then there's this one other point sitting out here. I don't know which cluster to assign it to. I could force it in one or the other, but maybe it's better to say, I'm not sure. It's 50% one, 50% the other. Okay, and there are some formulations which easily kind of extend to this. Or it could be that there are 3 really well-defined clusters, and then there are, with 1,000 points on them, and then there are 10 other points which are outliers that are kind of off. Do I really need to assign those to clusters? I'm not sure. Maybe I assign them partially to all clusters because I have no idea. You can do various things like that. So soft clustering is when you're not enforcing a point as in at most one cluster. Usually, it's given a fractional assignment across multiple clusters. Okay, so hierarchical agglomerative clustering. One more general thing I wanted to say about all of this. The other thing about clustering, about being this very kind of this objective, which is kind of very nebulous, and I haven't defined it precisely yet, other than the split width, is that if data is really well clusterable, that means it comes from different groups. It's usually any algorithm you run will work and will give you about the same result. If it's not clusterable, meaning that there aren't well-defined groups, or they're trying to find K, or you're trying to find 4 clusters and there aren't 4 clusters here, there are 3, most algorithms are not going to give that great a result, or maybe they give some different arbitrary result. So if it is well clusterable, most things will work. If it's not well clusterable, then it's not going to make too much difference. The main difference is in some subtleties in the distance functions, or in the sort of objectives that you have. Sometimes you want to favor certain situations like this picture here, this 2 moons, which is kind of like half moons. So these 2 moons picture, you want to favor something that's kind of looks like this, or some other objective. And then things can make a little bit of difference. Or you care about things that are easy to implement or work fast for your data set. So you may want to choose an algorithm which is very efficient. And so those are really going to be the main things to look for. Some subtleties in the objective functions and the efficiency of the algorithms, or maybe some extra structure that you get out of the cluster. So those are kind of going to be the things that you look for. Okay. Okay, so the hierarchical agglomerative clustering. I'm just going to write down the general algorithm, and then we can discuss it. It's very, very, very simple. First line is each data point xi is a starts out as a separate cluster Si. Each data point is its own cluster to start with. Okay, and then while 2 clusters are close enough, then we're going to do find the closest 2 clusters, Si and Sj, and we're going to merge Si, Sj into a single cluster. We'll call this Si prime. Okay, so this is inside of the while loop. Okay, and this is the whole algorithm, right? So while there are clusters which are close enough, then you're going to find the closest two of them and merge them together. So you're going to kind of find clusters that are close, and as long as you can do that, you keep merging them until you're satisfied and then you stop. Right, so just to draw kind of a simple picture here. Okay, so let's say this is our data set. And so initially, there are 5 points here. Initially, they're each in their own cluster. And then I'm going to say, well, points 1 and 2 are close enough, so let's make this into a new cluster. Then 4 and 5 are close enough, and these are the closest two remaining. This is going to be a new cluster. And then maybe S1 prime and S3 and data point 3 down here, maybe these are close enough. So I will now merge these together. Let's call this S3 prime. And then I can decide whether I stop. Maybe S3 and S4 prime, maybe these are close enough, maybe I merge them together. Right? So one thing you can see out of this is that if I write my data points like this, then I can think of kind of building a tree out of these data points. Right? So I can build this hierarchical tree of how I cluster them together. And this kind of tells me, and then this close enough version, maybe I decided I wanted to stop when I had 3 clusters, so then I essentially chop it off here. And so now I have these 3 different clusters. If I chopped it off there. But so this notion of close enough, sometimes you can wait until the end and then go back and do that. So you don't have to decide that right away. You can just run it until it's all one cluster and then go back and decide where was close enough. But it gives you this nice structure here in that not only do you have these clusters, but you have hierarchies of clusters within the clusters themselves. Okay. All right. But hopefully you realize there's this, if I told you to go and implement this algorithm, aside from, hopefully you can, one problem might be you couldn't read my handwriting, but it's written better in the notes. Hopefully it's not too bad. What else would you stop and say, wait, you haven't told me enough. How do I do that? Right? What's missing that I haven't told you yet? What is vague here?
The definition about close. The definition about close.
The definition of close, yeah. So one thing is closest. So I need to find the closest 2 clusters. There's someplace else that I mentioned a little bit. So I need to define how close are 2 clusters.
So what's close enough?
Yeah, in other words, what is close enough here? So I have these 2 vague things, right? This close enough, we'll come back to this. There's some interesting discussion there. The closest, so remember my input included a distance function between points, but now I need to say between clusters. I've got S3 prime and S4 prime. What's the distance between them? Or is let's say cluster S3 and S1 prime and S4 prime, which is it closer to? How do I decide which one is closer to? Right? So what's the close, between clusters? Right? So what does close mean when I'm talking about between clusters? So if it was just points, this is you know, we've discussed this. There are various distance functions here. But if I talk about between clusters, we haven't talked about that. So if there are sets, right? The clusters are sets, right? So we talked about the Jacquard distance between sets. Is that going to work here? Why is the Jacquard distance not going to work?
Because it assumes there's an intersection between two sets.
Yeah, if all the sets are disjoint, then they're all going to be distance 1. So the Jacquard distance doesn't help, okay? But we've got another distance between the points inside the cluster, so we need to somehow use that. What should we... Okay, so there are lots of right answers here. So what do you think is a good right answer for distance between clusters?
Distance from the average.
Okay, the distance between the average, so the average of the clusters themselves. Yeah, so I'll put this in a larger category. So create a center of each cluster, and then take distance between the centers, right? So how do I create the center of the cluster? Say the average, right? So one would be one notion of the center would be the average, and if I'm in Euclidean space, then I can always create say the Euclidean mean of the data, right? So if I'm using the Euclidean distance, the mean is well defined, right? But let's say that the data points now are going to be sets, like these are these bags of words, or these are these sets of k-grams that I have in a document. How do I create the average of these sets of k-grams? What does the average mean now? Well, if you don't have an answer, it's because it's a really good question. The average probably is not going to work in that case. For things that aren't, if you're not using the Euclidean distance or things that operate nicely on various manifolds, then usually the mean is not well defined. You can't just take a mean of data points if the data points themselves are sets. So if you can't take the average or the mean, then what should you use? The mode. But what if each of them, yeah, you could use something like the mode, which is the data point that occurs with the most frequency. But maybe they all occur once, right? Yep.
Could you pick the point that's most similar to all the other points?
Yeah, good. So so the average is the point that minimizes the sum of the squared distances, and we'll talk much more about this on Wednesday. But so pick the point S in Si, which minimizes, say, the sum of, we'll call this C. So S in Si, say the distance from C to Si, and maybe squared. Then it's going to look like the mean. And so you can do this just by checking all the points. Sometimes you don't want to check all the points because that's going to take a long time, so you'll sample some points and then whichever one from the sample you're going to use. And you're going to use as the representative, or there are other kind of ways you can not be as precise about this. So you can pick one of the data points which acts like the mean. And this is a pretty good choice. And as we'll talk more about Wednesday, maybe you don't want to use the sum of the squared distances, maybe just minimize the sum of the distances. Doing that, and maybe the mean, the average is the one that minimizes the sum of the squared distances. As we'll say in various things, this is more susceptible to outliers. If a point was in the cluster that really shouldn't have been, that's going to pull the mean over much more than if I just look at the sum of the distances. So maybe I don't want to square them. This is be a little bit more stable, but it can be harder to work with, as we'll see. Okay, and then if all of this fails, if you don't want to spend the time to do all this, all the points have the same weight, so the mode is not going to help. You can't compute the average. Picking the point that minimizes something is too slow. You can just pick an arbitrary point. So pick at random, pick the first one that you came across. Just pick one of the data points. Again, if the sets are well clusterable, the clusters are tightly grouped and separated, this will probably work as well as any other point, if you're lucky. If you're unlucky, maybe it causes a problem. So maybe you check a few data points and pick the one that minimizes some sort of objective. And this might work a little bit better. But even just some arbitrary point may work. Okay, so this is definitely a good option to pick a center. And all the class of algorithms we'll talk about Wednesday will be based on somehow having a center representative of the cluster. But what if we didn't want a center? What if there are certain issues with all of these? We may have had to resort to just an arbitrary point, which seems kind of, I don't know, seems kind of arbitrary, right? What if we didn't want to define a center? What other way could we define distance or closeness between clusters?
Distance from the closest points between two clusters.
Okay, good. So the distance to so I should say the distance between the closest points. So say distance between S1 and S2 is going to equal to the min of lowercase s1 and s1 and s2 and s2 of the distance s1, s2. So I take the two clusters, and so if we scroll up to our example here, I took the two clusters here and I took the closest 2 points, this one and that one there. That defines the distance. What sort of, I could have done similarly the distance between the farthest points. Right? I could have taken the farthest points between the two clusters. Right? This might also make sense. What difference between these objectives, what difference is this going to have? What sort of effect is this going to have on the sort of clusters I compute?
It's going to affect where the clusters form.
Yeah, so what can you tell me about where the clusters will form? How would that make a difference? What would an example of how this could change the result? Let's go back here. If I had a big whiteboard right now, this would all be out there, but we we are. So what difference would this have? So on this data set, it's probably going to be the same. Right? This one is well clusterable. It really doesn't matter what I do. If I look at this kind of crazy 2-moon data set, they're going to give different answers. If I use the closest distance versus the furthest distance, what would the difference be? How would the objectives change? So one way of thinking about it is if I was doing the closest distance, I kind of am drawing kind of a graph here. And as long as there's some short edge I can draw between these, then I can connect them. The ability to connect something depends on the closest edge I can draw to make it into a graph which is all connected. But if I'm using the furthest distance, it's getting sure that everything is close. That means every point is close to every, if the clusters are close, then I have to move them so every point is close to every other point. And so probably what I will do is I'll end up getting, so that the closest distance will allow you to get something like this famous 2 moons example. The furthest distance will probably end up with something like this instead. They shouldn't overlap. Maybe kind of like this. They might the shapes defining clusters don't even need to be convex. It's going to keep them very much more tightly grouped. So this is. The purple is based on the furthest distance, and the green based on the closest distance. So there's this branch of machine learning and data mining called that's called Manifold Learning. That was really hot maybe 10 or 15 years ago, and the idea was that really high-dimensional data is not really the high-dimensional. It lies in somehow lower-dimensional. They model this as a manifold. A manifold is this mathematical object that locally looks like its Euclidean distance. That means locally and so in this case, locally low-dimensional Euclidean distance. So in this case, you could think of, there's kind of like this one-dimensional manifold that describes each cluster. And that's all you need to make these connected. You just need them to be close to something else. And so this objective kind of worked with this manifold learning kind of thought process. Manifold learning. So this was cool. It kind of allowed people to do some stuff. There are lots even more stupider data sets, like there's this famous, this thing called the Swiss roll. So who's heard of the Swiss roll data set? Okay, it's this crazy data set where someone generated, where data essentially lies on a spiral, and they said, okay, you can learn the spiral. And this has been used hundreds and hundreds of times. Data does not look like this, but people could find this manifold structure that lied in there, and there was a bunch of data points on here. What happened was, this was cool, and if you kind of made up data sets like this, it could get to work really well. Then people discovered that there was noise in data, and this didn't really work so well. If you had noisy data, most data is kind of noisy. And so, there's a lot of the ideas from this kind of permeated into other areas. But manifold learning itself is often not used. There are some cases where data must lie in a certain way because it's been normalized. Like the cosine distance, normalize all the data so it lied on a sphere. And that's actually a manifold, and this kind of worked. but you have to have some very strong assumptions that are actually enforced about the data. If they're noisy, then all this kind of often breaks down. Under some small noise conditions, they can get to work, but so anyway, so if you wanted the closest distance, kind of followed that model, and the furthest distance, really restricted things are compact. It's kind of this change in the distance function has an effect here. So in these two ways to define the distance between clusters. There's kind of there's various other things you can do. I want to mention one other kind of general way to define the distance between clusters. And that is basically you look at some objective of the join cluster and you want that to be small. Okay, so that you want so it's kind of something like the density. So the distance is defined as the density of S1 union S2. Okay, so for instance, what would an idea of the density be? Well, let's say the radius of the minimum enclosing ball. So if the radius of the minimum enclosing ball is small, then the distance is small. So you're not looking at actually the distance between the clusters themselves, but you're looking at some objective on the union of the data sets. So things are easier to join if the cluster stays compact in some way, right? Or maybe it's the average distance either to the center or among the points after joining. So you join them and then you look at the average distance to the center. That's your distance between the clusters. Or you join them and you look at the average pairwise distance. That's your distance between clusters. So if you're thinking of two different joins, whichever one gives you the resulting cluster which is more compact, those are closer. So your goal is essentially keeping this width notion small as you're growing these things. And so you want to create the cluster which has the smaller resulting width. Right? So this relates to this notion of the width between clusters. Okay, so this is another way of thinking about this as well. Okay, so there are lots of ways to think of defining the distance between these clusters within this algorithm, and each of them in the same framework, each of them is going to give a different results for certain types of clusterings, but in general, if things are well clustered, they're probably going to work about the same. And this was just this notion of the closest. What was find the closest two clusters? All these objectives are reasonable things to do. And you can see hundreds of papers on different ways of defining this notion of distance between clusters. Maybe that's, now the paper is phrased, they say, here's the ultimate way to cluster, and basically it comes down to a different distance function in this algorithm. Okay, so now the other question that we didn't answer yet is, when are these clusters going to be, are they close enough? Oh wait, but before I do that, there's an issue with step 3, which are the closest two clusters. That comes up a lot in this sort of formulation. And it's often unspoken about, unspoken. Most people just ignore this. And that's if you have ties. So that didn't turn out. So if you have a tie, two clusters are exactly the same distance to each other. Do we really worry about these things? Well, you do if you're starting from clusters of size 1. They'll often be defined of a discrete nature. I'm drawing them again in Euclidean two-dimensional space. And often in Euclidean two-dimensional space, you assume they have continuous values, and these ties don't often happen. But when you have discrete data, when you're talking about something like the Jacquard distance between sets, ties come up. It's not that uncommon to have ties. And one kind of particular nasty issue about these hierarchical collaborative clustering is the choice of how you break a tie can drastically affect this resulting hierarchy. If I had chosen to put 3 with 5 before 4 with 5, it may have really differently, the hierarchy may have turned out very differently. So, so what should we do with ties? I don't know, this is one thing I don't have a good answer for. So it's kind of sensitive to this. You could try breaking them randomly and try rerunning it again and see if it changes a lot. It may not be sensitive, right? If the data is well clusterable, it probably will not change things very much. If data is not very well clusterable, it may have big changes. So if your data is all pretty much spread out and all looks pretty similar in all in kind of all of its kind of evenly spaced inside of a box or something, this could give you all sorts of different different results. So if that's the case, then maybe you say this data is not very well clustering. These small arbitrary decisions made a big difference, meaning this was a poor choice in the algorithm, or this was a poor choice to try and cluster this data. Some of you will do projects where your project will be to try and cluster some data set. And this has happened in past semesters, and it's usually at least one group comes back and said, we tried really hard to cluster this data set, and we couldn't, right? We couldn't find any reasonable clusters. This happens to a lot of data. You should not necessarily try and force clusters on there that's not there. It won't necessarily help. Sometimes you need to. Part of one good thing about clustering is that it's not just a modeling thing. It can be used inside of algorithms. Sometimes you want to do some sort of divide and conquer on your data. And so it makes sense to group spatially or similar points together and processing them. And there, it doesn't so matter. Maybe there are multiple equally good clusters with very different structure, but they don't matter for your algorithm as long as they both give a pretty good kind of spatial decomposition. And in that case, that's okay. That if there isn't any good clustering, but they still all give good spatial decompositions, they allow you to do the divide and conquer. Fine. Right? If you're doing quicksort on your data and it doesn't really cluster well, quicksort still works because you're able to divide the problem size. And in some high-dimensional stuff like these range searching or these nearest neighbor searching data structures, it didn't matter that it was clustering, but I still want to partition the data. So that's, oh boy, good. That was a close one there. All right, I was going on too long, I think, right? All right, okay. So let's get back to this last point. So what is close? What does it mean to be close enough? So how would I decide to stop this? What is the right way? We'll spend a little bit less time on this question. When would I stop merging together clusters?
You reach a certain number of clusters?
Yeah. You reach K clusters. Yeah, you're often told, I want K clusters, or you guess some value K. And when you get to K clusters, you stop. If you do this, someone will ask you, why did you choose that K? But maybe someone had a reason like, I've got a square, I want to divide into 4 parts and have 4 clusters for talking to the, my venture capitalist friends. you know. But yeah, you've reached K. Yeah.
Oh, would you do something with like like a sphere that develops all the data, then take some fraction of the radius or something, and use that as a
Yeah. Okay. So
like the range of your data? Like a
so
fraction?
like the radius of all clusters reaches a maximum, right? So if I merged any two clusters, they would get too big, right? Merging would get too big, or in other things, merging would get too big. Now I haven't specified what too big is, but maybe this is some quantity that you can understand. Instead of just some number k, I understand what 4 clusters means. I understand too big means that they're further apart than some quantity that makes sense in your distance metric. It's something that maybe makes more sense instead of, I don't know. So you might be able to put some number on that.
Here you mean radius of all clusters reach maximum. If we have a data is very far away from other data, I think it will never reach.
So you're saying if some data is very far away from other data points, then we may not have a good grasp on what this means. Is that what you're saying? Or are you asking like outliers are going to cause a problem? Or?
Like if a data is very far away from others, it would not be into some clusters. So the radius of that cluster will never become quick.
Yeah. So I mean, so the question is, the radius will never get too big, is what you're worried about.
Yeah, of that cluster.
Yes, so what the comment was, suggest this versus essentially some distance which describes the total radius of all points. If I put one ball that would describe the total radius of all points, let's say I wanted 10% of that radius. Right, so that way, if I were to include it so it's all one cluster, I know I would reach that value. Yeah, but there are some issues. Sometimes it doesn't make sense how to choose this threshold. And you need to be careful how you do it. So that's a good thing to watch out for. Yeah.
The size of the split between the clusters, if you want to define specific.
Yeah, so this seemed to be more about the width. Some notion of the width got too big. This is the split got too small. So maybe clusters got too close in some sense. They're going to kind of eat closer to each other. If they're too close, you would merge them, but there's some notions of split which are defined over the quantities in different ways that you could set something up like this. Yeah.
Well, I was going to say when doing a join, merging increases the average distance from the center or something like that. But then you never anywhere past the first one.
Yeah, often the average distance to the center, things like that, are always going to go up as you merge. Yeah, a lot of these things. Yeah, so I'll draw a picture in a second, but let's say you're going to have like the number of clusters, and you're going to have some quantity or like the inverse of the quantity, and they're pretty much always going to kind of look like this. So as the number of clusters gets smaller, some point is going to go up, or it could be the inverse of whatever quantity it is. So it's something like the average distance. So if this was, say, the average distance to the center, as you get fewer and fewer clusters, this is going to go up.
You're never going to get better than 1 point.
Yeah, so they're going to stay here. So it's hard to look at this for most quantities. So this is some, so some objective. And so one other one I want to mention is you have some density, and you've reached some threshold based on the density. So this other type of distance criteria I mentioned. And again, this is going to happen again. This could be a density thing. The density is going to get smaller and smaller as you keep merging typically. There may be a few little bumps in here, but in general, this is going to happen. Yeah.
So would you define density as the number of points within a cluster, or would that be defined as the number of points in a given space?
You know, you could do something like the ratio of the number of points to the volume of the smallest ball that contains all the points. There are various ways you could do this. There's very notion of density, yeah. A lot of them are going to have this sort of objective. There's one objective that we'll talk about towards the very end of the semester called the modularity. And this is often not used in this partition idea of clustering, but in finding these kind of anomalous regions which are really well concentrated. And this modularity concept is not going to look like this. It's going to have an actual minimum at some point. And it'll kind of tell you where to stop. And there are a few objectives you can sometimes get like this, but there is usually hidden or not so hidden so parameters. So all of these essentially have some parameter that tells you. Either I was too wide, I got too small, there's some density threshold I reached, some value k. There's some threshold that I'm somehow telling you when to stop. There's not some magical way to do it. Modularity kind of gets around this, although if you squint at it in some ways, you can kind of see that they did make some choice, which seemed very reasonable inside of it, but if you could have maybe put a different number other than 1 in some place, and it would still make sense. And so there's a parameter that was 1, and so you don't see it because it's a coefficient of 1 someplace. But 1 is the one that makes sense, and a lot of people use this modularity in finding these community using graphs. So now if you look at this chart though, it kind of seems like there's some region right here which seems good. If I get many smaller than this, it kind of shoots up. This is not uncommon, and this spot is often called the elbow. Let me try and write that a little bit better. So it's like the elbow of my arm, right? So kind of this way, right? It starts shooting up right here, so maybe I want to pick this number of clusters. If you plot some objective function, it'll often look like this, and you want to pick some point around here. That's often, it's kind of, seems like very ad hoc and weird, but this is often not a bad thing to do. So if you can plot this, and with the hierarchy, you kind of are always maintaining this value, so this is kind of often a useful, reasonable way to do this. Okay, so again, I don't have a good answer. This is again a modeling choice. It's not like in the algorithms class where you're given a very precise thing. Here, you're making all of these decisions, and they all affect the outcome. Again, this is useful because these decisions often, for data where you would expect a good clustering, these decisions usually don't make that much of a difference. But they can, in some cases, make some small differences. Okay. Any questions on this? On what does close mean between clusters?
Can I explain objective here?
The objective. So some objective would be, so like we talked about the, like this width, the merging would get them to be too big, right? So in this case, as you go the number, so if you're looking, it could be a variety of things. It could be like the average distance from the center of the cluster. As you got smaller number of clusters, the average distance is going to go up. When you have n data points and n clusters, this objective is 0.
So we can choose objective between this kind of thing.
Yeah, so each of these somehow gives you some sort of objective. If you want to look at the density of the clusters, maybe that's the ratio of the number of points to the average distance to a point, or the furthest distance from the center, or maybe that's squared or something, depending on what dimension you're in, right? But there's some notion there are various notions of density you can use. you could, and then this notion of split, you want the split to be small, so maybe this is 1 over the split then. And that's going to work better. You somehow, if you want to draw a picture that looks like this, as the number of clusters gets smaller, you want the objective to go up. So you're balancing the number of clusters, kind of the tighter the model, the simpler the model you're producing versus how poorly it models the data, right? Your idea is as the objective goes up, the model of the data is representing the data worse. You know less about the data from just looking at the clusters. All right. Okay, so one last thing to talk about for this lecture is the efficiency of these algorithms. How long does this run? So the runtime has a function of n, where this is equal to the size of the input data. All right, so runtime is a function of n. How long does it take to run these algorithms? Okay, so first thing, let's assume we merge to a small number of clusters, right? So we start large, but we eventually want this to be small. So let's say, for instance, that let's just run this all the way to the end and figure out when is enough later, right? So how many merges? So how many merges do we have? How many times do we perform this merge operation? So, okay, so here's a, okay, yeah.
So would it be like roughly log n or n log n? Or?
No, it's log n or n log n, so it's...
n log n, meaning you have to go through you have to see each data point at least once and then you merge.
Yeah, so I'm not talking about the time. Yeah, I mean, you're starting to get in the right direction. So how about I ask a different question? Maybe you've seen the answer to this. How many, if you have a basketball tournament with 64 teams and it's single elimination, how many games do they play? 63 games. Each team loses once, except for the team that wins, right? So if you have n teams, you basically play O of n games. Every time you merge a cluster, your number of clusters reduces by 1. You've got rid of one cluster. So you're going to need O of n merges. Now you might be able to optimize this. You somehow say there are a whole bunch of things that are close and I can merge all of them in one step. But they can be tricky sometimes because you need to find an independent set of things to merge. You don't want to merge one cluster into 2 other clusters at the same step. So you need to be a little bit careful that you can't do this together. So you have to do O of n merges. And so, well, let's kind of look at the naive version where each round you just merge 2 clusters together. So there are O of n rounds of this while loop. Like if we go back to this algorithm up where over here. We go back to this algorithm here, right? Go back to this algorithm. This while loop basically has O of n steps. Right there, O of n steps here through this while loop. Okay, so now merging them, let's not worry about merging them. We need to find the closest 2 clusters. How do we find the closest 2 clusters? And how long does that take, right? The merging, it turns out, we'll be able to do as fast as find the closest 2 clusters. So how do we find the closest 2 clusters? how long does that take?
Depends on his closest criteria.
Yeah, so, right, so let's take one where we do something simple that we can do fast. Yeah, so let's pick an arbitrary point. Right, so that takes, each closest computation takes constant time, right? We have some center or we have some arbitrary point. Turns out if you want to maintain the average and you merge two clusters, you can update that in constant time, right? You just average, do a weighted average of the two centers. You can do that in constant time. So okay, so it takes let's say it takes constant time to measure the distance between two clusters. So how long does this take still? The closest two. This.
So that n squared, except like Cartesian, like all the.
Yeah, so I mean, if you're not doing anything clever here, there's O of n squared of these comparisons, right? So at the very beginning, so for the first half of the merges, you have at least n over 2 clusters. So you have to do n over 2, choose 2 is still O of n squared. So for the first half of the merges, you have an asymptotically large number to check. So if this takes constant time to tell the distance, it could take more. It could take n squared time to tell the distance, but it turns out then the other clusters would be small if you're at that step typically. But let's say if it takes constant time for each of these, this is O of n cubed. Because each round you need to spend that much time. Now if you're clever, the thing is only two clusters are destroyed and one is new one each round. So most of the distances you're computing are staying the same in between the rounds. So there are n squared distances, but only O of n of them are changing. So if you're careful with a priority queue, where you maintain a priority queue of the distances, you can update this in log n time, and then you only need to remove out the O of n ones that are with clusters that no longer exist and add in O of n more. Each of those takes n log n time for all those operations, and then you take the top off the priority queue. You can turn this into O of n log n, assuming that you can calculate the distance in constant time. If that takes longer, then this is going to take longer. If it takes longer, you probably can fold it back into the O of n squared without increasing that, because you only need to update O of n of these. So if it takes linear time to compute your distance, then that's better. That's okay. Then it's still O of n cubed. Now if it's the all pairs distance, you want to calculate the distance between all pairs of points to all the pairs in the other cluster. This one might take longer. But in general, it's either O of n cubed or n, in this case, it would be O of n squared log n. And it turns out this is a big number. This takes too long. This is usually going to be slow. When you run this on a lot of data, this is going to take a long time. So if you use this for your project, every year someone comes back and says, we tried to run higher group clustering on it, and it took too long. These algorithms are not efficient. There are some ways you can somehow play with the number of merges, try and merge some things together, but this usually leads to problems if you try and be too clever about it. If you try and do too many at once, you try and merge two things together, or you end up making more arbitrary decisions, which affects the modeling. So this is in general fairly slow. The ones we'll look at in the next two lectures either are directly faster than center-based or can be made faster using some advanced techniques, the spectral ones. All right, so that's it for today. We'll talk about the assignment-based clusterings on Wednesday.